Swayam Prabha. Digital India. Educated India.
I'll use a low voice, so just cooperate with me. What is this? Okay, so there is a pair of pliers. Pliers, no. Here. Just to make sure that I am safe, I'm holding it now and I'm going to heat it. I'm going to heat it. What will happen? It will expand, correct? It will expand, and as it cools, okay. So let's see. Yeah, but probably it is expanding, but very small extent. Yeah. So let's do something where it expands more. So we'll take some other material. Okay, so we'll take some other material and heat it. I don't know, so material is different. Oh, it expands now. Oh, good. Good. It's expanding quickly. It's expanding quickly into a spring which is longer, correct? It has expanded so much. You can see it, right? As I heat it, its thermal expansion coefficient is very, very high, right? Okay. So let's see. How about where do I have the other one? Okay. Let's see the expansion coefficient of this one. Okay. Any guess? That was very large, correct? Why do you think it shrinks? Oh God, you're like Pranav now. Oh God, you're now. I'm becoming predictable now. It's 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 contracting. It's not thermal expansion, no. If it is thermal expansion, it is negative thermal expansion. I can't call it as thermal expansion, thermal contraction, right? The question I have is, I know what is thermal expansion. What is thermal expansion in terms of what happens at the molecular level? Atharv is ready. Yeah.
When you heat it up, the kinetic energy of the molecules, as the temperature increases, the kinetic energy.
They dance a lot more. And therefore they need more space. Very good. Very good. See, understand in such a way that you are able to catch it. Yes, you can translate that to kinetic energy, etc., etc. It is just dangling more. When it is dangling more, it doesn't want people nearer, and therefore it expands. Correct? But how come it's contracting? Contracting is very, when the temperature is increased, it should be dancing, which means it needs more space. It should expand.
So it has a higher kinetic energy and it expands, but the surrounding material pushes it towards.
Not necessarily. It's the same material throughout.
Negative kinetic.
Negative kinetic energy. Anybody else? Anybody? Molecules are very small. Yeah, but that's the case with the first one also. There is no difference. Yeah.
There is the energy that we give by heating it used as the energy required to compress this thing.
Yeah, but how can it be compressing when I know thermal expansion is directly proportional to the increase in temperature? Correct? Directly related to increase in temperature. It could be proportional or need not be proportional.
Before that, will after it cools down again, will it expand?
Yeah, look at this.
So can we write,
Where is that? It's the same.
so can we write inelastically compress it and then heat it?
Yeah, it's a shrunk. See, look at this. Wait, let me just.
So can we?
You're trying. We will do later. But what is the principle behind ice?
Like, sir, when you melt it, it actually
Huh.
contracts and
Huh.
like generally wax.
You mean the volume comes down? Is that what you're saying?
Its expansion decreases. Doesn't expand. It actually decreases.
Okay, very good.
So I think it's not even like we are trying to explain this using something thermal expansion, but I don't even think we can explain it using that.
Okay, so what you're saying
So
is
because-
we cannot explain using thermal expansion.
Because, for example, it is like adding on to what I think Athar is trying to tell also.
Not her. Huh?
I wasn't done.
Hey, what? Okay, what is like for example, if it was thermal expansion, once it has cooled down back, it will go back to its original state of being before it heated it.
Yeah.
But it has not gone back to the original state.
Same.
No, it was originally bent, like expanded.
Yeah.
So is it like when you heat it up, the molecules wiggle more and they find the space where what do you call that, closer packing is available. So afterwards,
Okay.
even after they cool down, they settle
Got it.
at that place.
Yeah.
So this is what you were talking about smart metals return to their original shape and Nike this is the original shape of the
This is the original shape.
shape and the
So whatever I do, it will come back to this shape. Is that what you're saying?
Yes, yes.
Huh? Why here? Why should it? See, for example, if I take ice, you said ice, no? Ice, I melt it, and then when I again cool it, it will become something else. Yeah. So where is the question of change that we are talking about? Shape of the material there.
is this like a smart material?
We call this as smart material.
So sir, I think what happens is
You-
transitions between different crystal structures.
Fantastic. So what really happens is, just like what each one of you said, it is not thermal expansion. The first thing is, we understand this to be not thermal expansion. It is some other phenomenon that is occurring over here. As she pointed out, and both of you also added to it, it is changing from one state of the material to another state of the material. Got it? When ice turns to water and back, the state of the material goes from solid to liquid. This is not liquefying. Correct? But what happens is, it changes from one crystal structure to another crystal structure. Right? This change in crystal structure influences the change in volume. Got it? Right? This change in volume is directly related to what you see here. There are two states. One state we usually call as a parent state. Parent state. Parent state or home state, where it remains in the same shape that it had before, because you're returning to home. Right? You may be going to a hostel, you may be going to something else, right? You may be probably taking another room, but we keep shifting all this. But the moment I heat it, it comes back home. And this is its home. Is this clear? We call this material as a material that remembers the shape, remembers home, remembers home. This is its home. Okay? After my retirement, I am not going to be in IIT. I have to shift my home. So there is a possibility of shifting my home also, right? So I'm going to talk to you about shifting my home also later. But the fact of the matter here is it is going from one state to the other when I deform it, right? When I deform it. I'll come to it. When I deform it, it's unlike eyes. When I deform it, it goes to another shape, and when I heat it, it comes back to its home state. Yeah, home state. Yeah. Now you may be asking this question about eyes. Now, she asked a question about skates, right? Ice is also similar to this. How is it similar? It is influenced not only by temperature, it is also influenced by stress. Both stress and temperature play a role in terms of its state. Am I audible?
Yes, sir.
Right? So I can either use temperature or I can use force in order to change its shape. So far it's clear?
Yes, sir.
Yeah?
So how is this smart material different from an extremely elastic material?
So what is a smart material? A smart material is one which is used in an application that is smart. For example, let's say you go to kitchen and there is some sweet on the stove. You go touch it. What happens to you? What happens to you?
You come back, you go back.
Huh?
You back away.
You back away immediately. Because your hand is smart enough. My God, I'm not able to.
So you can take a break.
Take a break.
So your hand is smart enough to retract. What really happens in this is your muscle is a smart material. It responds to a signal that the brain sends it, right? Once it gets the message, it retracts. You also know about what is called,
So you can take a break.
whenever I use R, it becomes reflex action. Heard of it?
Yes, sir.
Reflex action. What actually happens to you when you touch that hard object is a reflex action. It doesn't go to brain, but immediately muscle responds to this. muscle muscle responds to the stimulus directly, right? So we define a smart material as material which is used in an application which is smart. It doesn't have to wait for somebody to tell, oh, remove your hand. Correct? It has that smartness to remove its hand directly. Got it? Madam, is it possible to shift? Vijayalakshmi, madam. Unable to. Shall we shift to some other day? Is that okay? No, I'm talking about. I'm not able to. Finding it difficult. and they are also not enjoying it. Don't know, but I've had many workshops of 6 hours and all those also. The first time I'm having this, but it doesn't matter. Okay, so I'll do one thing. I'll request Dharmi and Ainul to show some other materials, and then I'll come back to this. Okay? Good. Okay. Go ahead, Dharmi. Thanks, folks. Yeah. Can I also ask questions?
This one also I'll hook you in the call. It's a backup mic actually.
Okay.
Okay guys, good afternoon. About to noon. So as sir already explained,
I know it's in the middle stage of his research. He is working on printable composites, 3D printable composites. Composites. He's going to explain what is a composite. Okay?
what class you are in? 11th or 12th? Okay, transitioning to 12th class. So you must have already heard about magnets. Yes. Who can tell me how magnet works? How it works? What happens inside the magnet? One at a time. Yeah, you tell me.
Oh, so they have this thing called electron spin. So when the spin is different, that actually changes the magnetic properties. So that changes that from one direction to another direction. So they fly and not.
Okay, so can you give me one example of a magnet? Which material shows the different behavior you are telling? Huh? Nickel. Okay. Nickel. Okay, fine. Now, what like you have heard of magnets, right? So, how many type of magnetic materials are based on their magnetic property? Huh? Three. Okay. What is the difference between all those?
The level of magic is different.
In terms of what?
In terms of their strength.
In terms of
Strength.
what strength? What do you mean by strength?
Strength. Force.
Okay. How many poles a magnet has? Hmm? 4 poles. Are you sure? Okay. Next question. Have you heard of permanent magnets? I have here. You guys have, like, I feel like you are school guy people, so you are very curious. You must have opened some radio or something and must have opened a speaker also, right? Have you seen some black circle around in the speaker, and whenever you bring it near to any metal surface, it stick to them? Why? What type of magnet? What material it is made of?
Iron.
Okay, so you are saying that iron can be made into a magnet. Okay. So, yeah. So this cutting plier is made of iron. Who is here can convert this into a permanent magnet? You just said na that the speaker magnet is made of iron, right? Yeah, but you just said that the speaker magnet is made of iron. So I am having iron, convert this into a permanent magnet like this. This is a permanent magnet. I'll come to the material. I'll come to the material later. I'm talking now. I don't have any energy sources. I am having a block magnet in my hand, and this is a magnet. If you don't believe me, I cannot directly because it's very strong. So I'll just stick from the back side. See, okay, it's sticking to it. Can I? You just said now that the speaker magnet is made of iron. Who here can convert this plier into a magnet? I'll give you 1,000,000 rupees to that person. Whoever can convert this plier into a permanent magnet. Temporary, anyone can make. All I need is a battery and a solenoid. No, you cannot attach a magnet. I am telling you, it should have its own magnetic field like the one I am having in my hand. Yes.
Maybe we can try stroking this large.
I am asking about a strong permanent magnet like this block. You want to know the strength of this magnet? It can, if I hang 30 kg weight over here, it can still. Yeah, I'll come to that. Okay, who here can tell me how do you measure the magnetic field? What is the unit of magnetic field?
Tesla.
I don't know what is Tesla. Any smaller unit? Okay. In energy terms, in terms of energy, yeah, in joules. So, how much 1 Tesla is equals to? In terms of Gauss? Huh? 10 to the power? 10 to the power minus 10 to the power 4 Gauss. Okay. So, let's say I want to convert this plier. You said it is a permanent magnet you can create. I want it to have let's say 1000 Gauss per magnetic field. Who here can convert this into a permanent magnet? Why can't? Why you cannot convert this plier into a, I have my question now, next question. Why you cannot convert an iron plier into a magnet?
It does not hold the Tesla.
Why?
It have its own dipole.
Because Earth itself, the apps.
I'm not going to Earth. We'll come to that later. We are talking in the terms of material right now.